प्रोफेसर कांत, एक सेकंड में आप 1 मिनट बाद अगर इसको शेयर कर पाए, अभी एक बार
formally live. Formally, we can start this program of Engineers Day. With your kind permission, shall we start this program?
Yes, please go ahead.
Okay. Good morning to one and all present in this program of Engineers Day. On the occasion of this auspicious day of National Engineers Day, I, Dr. N.D. D'Souza, Associate Professor, Nirwan University, on behalf of Nirwan University and Indian Institute of Materials Management, Jaipur, welcome you all the delegates, participants, and esteemed members present in this webinar entitled Air Pollution, its Management and Control in Thermal Power Generation. 15th September is celebrated in India as an Engineers Day to honor the birth anniversary of Sir M. Viswesvaraya, more commonly known as Sir M.V., born on 15th September 1860, the first engineer of our country. Sir M.V. was not only an Indian civil engineer, statesman, but also 19th Diwan of Mysore, serving from 1912 to 1919. The Indian government honored him with the country's highest civilian award, that is Bharat Ratna, in 1955. That was, of course, in independent India. During the era of pre-independence, means when British Empire was there, Sir M.V. was knighted as a Knight Commander of the British Indian Empire by King George V for his contribution to the public good. On the occasion of National Engineers Day, we are having our renowned guest speaker, Professor Keshav Kant, ex-professor, Department of Mechanical Engineering, IIT Kanpur, to share words of wisdom on air pollution, its management and control in thermal power generation. I would like to invite Professor Ravi Kumar Goyal, Pro-President and Registrar, Nirwan University, Jaipur, and Chairman IIMM Jaipur to welcome our esteemed guest for today's program. Over to you, Professor Ravi Kumar Goyal, sir, please.
Thank you, Dr. D'Souza. So, good morning, everyone. Happy Engineers Day.
Happy Engineers Day.
Thank you, sir. So, there is a say that scientists dream about.
Happy Engineers Day.
Engineers do that.
Happy Engineers to you also.
Thank you, sir. So, first of all, on behalf of Indian Institute of Material Management, Jaipur, and Nirwan University, Jaipur, I welcome Chief Guest and Keynote Speaker of today's webinar, Professor Keshav Kant, retired professor from IIT Kanpur, office bearers and members of Indian Institute of Material Management, my fellow colleagues of Nirwan University, Jaipur, other dignitaries, and friends on social media. I welcome you all. IIM Jaipur and Nirwan University Jaipur has started this webinar series, and IIM Jaipur, Indian Institute of Material Management, is having more than 10,000 members and 52 branches in the country. And the Nirwan University Jaipur has been incorporated by Act number 2 of 2017 of Government of Rajasthan, and it is running various certificate, diploma, advanced diploma, UG, PG, and doctoral program. Once again, I welcome everyone on this very important webinar on air pollution and its management and control in thermal power station. Thank you. Thank you so much.
Thank you, sir, for your precious time and nice introduction. We all know today's era is depend on energy. We all know that due to increasing demand of electricity, the power generation companies are more focusing to generate more power to cater the requirement of public. Thermal power stations are major players in power generating resources, causing the air pollution and different radiations in the environment. Our today's speaker, Professor Dr. Keshav Kant, has rich experience of 38 years from 1967 to 2005 in IIT Kanpur. Presently, sir is serving as consultant to Rural Technology Action Group of PSIT Kanpur. Sir was awarded various awards such as Outstanding Engineering Services to Society Award 2021 in 15th August 2021 by the Institution of Engineers Rajasthan Center Jaipur on the occasion of 75th Independence Day of the country. Sir was invited speaker in various abroad universities such as Tokyo University, Hong Kong University, and so on. Sir has various contributions in the sector of power generation and has rich experience on the topic of air pollution. Sir has also invited as a guest speaker at McGill University, Calston University, and New York as well. Sir has contributed his rich experience with speakers at national and international level in various national and international conferences. Now I invite to Professor Keshav Kant, and we wish to have a great discussion on this panel. Over to you, sir. Now you can lead the program, sir.
Thank you, Professor, for the nice introduction. Thank you, Dr. Ravi Goyal, and I like to thank Dr. Ravi Goyal and his organizing committee to have invited me for this particular webinar series in this area of air pollution. I'm grateful to him and his members of the organizing committee. I will be talking about air pollution, its management and control in thermal power generation. I'll be talking about sources of air pollution, effects and strategies, suspended particulate matter, NOx reduction, SOx reduction, mercury pollution, electro-catalytic oxidation, air quality management systems, and then finally conclude my seminar. Air pollution, as you know, is the presence of contaminants in the atmosphere, in the atmospheric air, in concentrations harmful to humans, animals, plants, materials, and environment in general. Air contaminants may be gases, vapors, suspended particulate matter, bacteria, virus, fungi, spores, pollens, aerosols, excessive sound, nuclides, radiation, excessive heat, thermal pollution, fine particles of toxic materials, heavy metals, etc. Sources are natural causes which cannot be controlled, and there are anthropogenic causes which can be controlled, and we must pay our attention to the anthropogenic causes. Anthropogenic causes of air pollution are various industries, fossil fuel burning power stations, surface transports, aviation, shipping, waterway transports, nuclear power stations, mining of various ores and materials like coal, lignite, etc., transport of mined products, their refining, manufacturing, and use. Pollutants emitted by the thermal power plants are coal dust, carbon dioxide, other gases like SOx, NOx, ozone, fly ash, particulate matter, hot water treated with chemicals like chlorine, heat, radioactive substances, other chemicals like arsenic, heavy metal residues, including mercury, chromium, acid rain, etc. If you look at some of the statistics, in 2011-12, India's 111 steam power plants consumed 503 million tons of coal and generated 580 kilotons of SPM, less than 2.5 microns in size, 2100 kilotons of sulfur dioxide, 2,000 kilotons of NOx, 1,100 kilotons of carbon monoxide, 100 kilotons of VOC, and 665 million tons of carbon dioxide annually. Air pollution control refers to the techniques employed to reduce or eliminate the emission into the atmosphere of substances that can harm the environment or human health. The effects of pollution are: it causes environmental degradation, affects human health, causes global warming, depletes ozone layer, makes the land infertile, and damages crops and trees. Strategies for reduction of pollution are: control of generation and emission of pollutants in various processes, conservation of natural resources, reduction and waste of energy and materials, recovery and recycling or utilization of the waste products from the processes, reduction of leakages or inadvertent escape of polluting gases or vapors, selection and use of efficient processes and machineries, raising efficiency by required modifications, better maintenance and operation practices, achieving optimum combustion efficiency to reduce fuel consumption using less polluting fuel, utilization of solar and wind energy for generation of power in industrial and domestic sector. Suspended particulate matter is emitted from the stacks of fossil fuel fired thermal power plants, coal lignite handling plants, fuel pulverizing plants, ash handling plants, etc. It is also emitted during mining, handling, and crushing of coal, lignite, stones, ores, etc., mainly material dust, also emitted in nature by volcanic eruptions, jungle fires, and dust storms. Respirable suspended particles or respirable particulate matter, RPM, is the final part of suspended particulate matter, which is less than 10 microns in size. It is respired along with the air, causing many ill effects on health of animals and human beings. Particles of size less than 10 microns in size do not settle down and therefore remain suspended. They enter lungs with air inhalation. These fine particles do not come out during exhalation. The RSP or RPM may contain fine particles of toxic materials, solid or liquid, of heavy metals including lead and its compounds. If you look at the percentage of respirable fly ash particles from stacks of coal-fired power stations, as the size of the particles decreases, the percentage respirable increases. For 2 microns, it's almost 100%. For 5 microns, it's 25%. And for 10 microns, it is 0. So as the size of the particles decreases, the percentage respirable increases. Similarly, percentage deposition increases with the reducing size of the particles. Some examples: the smoke from burning of fuel oils may contain compounds of vanadium, sulfur, aluminum, silicon, and lead. Diesel oils may contain compounds of lead, vanadium, sulfur, fluorine, chlorine, etc., besides sodium, potassium, calcium compounds, which may be present in all fuels. The smoke of solid fuel like coal and lignite would contain compounds of sulfur, iron, titanium, phosphorus, silicon, aluminum, manganese, chromium, nickel, mercury, calcium, sodium, potassium, chlorine, and fluorine. Effects of SPM. Suspended particulate matter causes the dust deposition on all things and is a great nuisance. The RSP or RPM, that is respirable suspended particles, is a great health hazard, especially for respiratory organs of human beings and animals, and may cause many diseases. Inhaling of silica dust causes silicosis. Inhaling of asbestos dust causes asbestosis. Breathing of air laden with coal dust causes anthracosis. inhalation of iron dust or other metal dust causes siderosis. Toxic metals, they adhere to the fly ash, and as the size of the particles, this table basically gives you the size of the particles 25 microns, 12.5 microns, down to 1.5 microns. And the toxic elements in traces are vanadium, lead, nickel, manganese, iron, copper, chromium, cadmium, beryllium, boron, and aluminum. Their amounts adhering to the fly ash varies depending upon the size of the particles. As far as the World Bank guidelines are concerned, all new plants or units should have SPM not more than 50 milligram per normal cubic meter. Specific attention has to be paid to SPM less than 10 microns in air. If you look at the characteristics of various dust collecting equipments, battery cyclones can be applicable to particle size more than 10 microns, electrostatic precipitators to any size less than 1 micron. In fact, any size of particles should be greater than 1 micron. Baghouse can be applicable from 0.5 to 1 micron. The pressure drop in each case varies. The degree of cleaning is also different. For battery cyclones, it is 80% for particles below 20 microns, 95% for particles above 50 microns. 80 for electrostatic precipitators, it's 80% to greater than 99% on all particles. And for baghouse, it is 95 to 99% on particles below 5 microns. Now, we will talk about NOx reduction. Measures for NOx reduction are in-furnace reduction of NOx, that is internal to the boilers, and then we have some measures as for post-combustion reduction of NOx also. As far as the NOx are concerned, first of all, what exactly is NOx? Sum total of all oxides of nitrogen are called NOx. This may include nitric oxide, nitrogen dioxide, N2O3, N2O4, N2O5, and it is expressed as ppm of NO2. Most of the NOx in the atmosphere is in the form of NO and NO2. NOx is emitted during combustion of fuels at high temperature in gas turbine power plants, boiler furnaces of fossil fuel fired power plants, industrial boiler furnaces, incinerators, coke ovens, etc. These nitrogen and oxygen, they combine to form NO and make other compounds N2O5 or NO2. And NOx may combine with moisture to form nitric acid or nitrous acid, HNO2, and a large amount of 250,000 tons per day of acid may be formed in this way. But the idea is that we have to control NOx. This NOx is about 25 to 30 kg of NOx per ton of petroleum products, 5 to 10 kg of NOx per ton of coal. Emission of N2O is prominent during low temperature oxidation of fuels, that is during spontaneous combustion in coal stacks. Now there are methods, several methods of controlling NOx inside the boilers. One of them is low NOx burners, and these are a special design of fuel burners called low NOx burners, and they can reduce NOx emission during the combustion by about 30 to 50%. It's a fuel-rich burning in low excess air. Combustion of the remaining fuel or carbon monoxide is completed by providing overfire air. Pulverization of the coal has to be finer, about 149 microns, to reduce the carbon in fly ash. The other method would be flue gas recirculation. Flue gas recirculation in gas and oil-fired boilers can be used to lower the furnace temperature to suppress the NOx formation. In case of coal firing, FGR, flue gas recirculation, is not favored mainly because it causes severe erosion in the flue duct, dampers, recirculation fan, etc. involved in the FGR system. Another technology to reduce NOx is the reburn technology. Reburn technology has three zones. One of them is the main burning zone, which burns up almost 80% of the fuel with a stoichiometry of 1 to 1.1. That is very low excess air. And the second zone is the reburn zone, which burns 20% of the fuel gas, oil or coal, over the main burning zone. Its stoichiometry is 0.85 to 0.95. That is, it's a reducing atmosphere. Then overfire air is supplied over the reburn zone to complete the combustion. The hydrocarbons generated in the reducing atmosphere react with the NOx from the primary zone, and substantial decrease in emission of NOx results in the reburn process. Increase in the flue gas site corrosion or slagging may result. Selective non-catalytic reduction of NOx. In this case, we inject ammonia, and this ammonia combines with NO to form nitrogen and water. These chemical reactions are given in this slide. NOx reduction by FBC technology, fluidized bed combustion technology. Coal-fired boilers based on fluidized bed combustion generate much less NOx as compared to pulverized fuel boilers. Atmospheric fluidized bed combustion or circulating fluidized bed combustion boilers may have about 225 to 400 milligrams per normal cubic meter of NOx emission. Pressurized fluidized bed combustion uses combined cycle plants and can achieve NOx emission values less than 140 milligrams per cubic meter. We then talk about post-combustion of NOx. In post-combustion, we again inject ammonia in the flue gases along with the catalyst, and the nitric oxide combines with ammonia to form nitrogen and water. These chemical reactions are also given here in the slide. The catalyst is titanium dioxide. Reduction of NOx is 70 to 90%. Other catalysts are vanadium pentoxide, tungsten oxide, molybdenum oxide, and there is a NC300 zeolite-based proprietary catalyst which is also used. Selective catalytic reduction reactors are placed after the hot side ESP before the air preheater. Urea-based systems can eliminate 90% of NOx. Wet scrubbing of the flue gases is not used for NOx control. This table here gives you the NOx emission by different types of boilers: traveling rate, spreader stoker, wall-fired boilers, tangentially fired boilers, PFC boilers, and PFBC boilers, pulverized fluidized bed combustion boilers, and pressurized fluidized bed combustion boilers. And the last one, the minimum 140 milligrams per cubic meter. Other values are quite high. We now talk about SOx, the sulfur oxides. This SOx is a mixture of sulfur dioxide and sulfur trioxide, which is emitted by burning of sulfur and its compounds. Fossil fuels, coal, lignite, and petroleum fuel oils contain sulfur compounds. SOx emission is more acute with oil firing than with coal firing. Emission sources include thermal power stations using solid or liquid fuels, industrial boiler furnaces, other industrial furnaces, combustion turbines, etc., using fuels containing sulfur. Generally, non-coking coals available for power generation in India have low sulfur, 0.2 to 1.1%. Coals of northeastern region are higher in sulfur, more than 2%. Light diesel oil has 1.8%, high-speed diesel has 0.4 to 0.5%. SO2 is fully oxidized to oxygen. SO2 is fully oxidized by oxygen to sulfur trioxide in presence of catalytic agent, and the reaction is exothermic. Absorption of SOx. Indian coals have a low amount of sulfur. Calorific value is low, and therefore the consumption is high, and amount of SOx is significantly large. SOx, which is mostly sulfur dioxide, remaining sulfur trioxide, and other oxides of sulfur. There are three ways to control SOx emission from boilers burning fossil fuels. One is absorbing SOx internal to boiler. The second is absorption of SOx from flue gases on exit from the boiler, called post-combustion absorption systems. And the third is control emission of SOx by refining the fuel to lower its sulfur content. FBC technology has fluidized material bed cover. FBC boiler has a hot fluidized material bed over which coal or lignite is continuously fed along with limestone. SOx is generated, reacts with lime in the bed material, and gets retained in ash, mostly as calcium sulfite or calcium sulfate. These chemical reactions are given here. In furnace, SOx and NOx, absorption by FBC is a good option for minimizing air pollution. Control of SOx emission by in-furnace absorption systems for steam generators is preferable, as it takes care of NOx reduction also. Much cheaper than post-combustion fluidized fuel gas desulfurization systems, flue gas desulfurization systems. Atmospheric fluidized bed combustion boilers work on Rankine cycle, while the pressurized fluidized bed combustion boilers work on the combined cycle. Post-combustion of SOx removal, large number of power plants are still using pulverized fuel boilers. Flue gas desulfurization becomes essential for post-combustion removal of SOx. Number of FGD processes have emerged with new techniques of improving SOx removal efficiencies. Suitable FGD technology is available for power plants using any type of fuel, including Indian coals or lignite. These FGD processes can be of two types, non-regenerative and regenerative. In the case of non-regenerative, the solvent is not recovered. In the case of regenerative process, the solvent is recovered and reused. Limestone gypsum process, flue gases after passing through an ESP, cooling and washing, go to an absorption tower where limestone slurry is sprayed. SOx reacts with slurry and are converted to calcium sulfite, calcium bisulfite, or calcium sulfate. We now talk about mercury pollution. Mercury and its compounds are highly poisonous. It is released in gaseous form when coal is burnt. Mercury emission is a real threat from coal-fired boilers. Mercury is volatile, and elemental mercury directly pollutes air. Also, mercury and its compounds are converted to solid phase and are emitted as RSP, respirable suspended particles. Water from scrubbers, ash handling may contain some mercury, which may also pose some problems if not monitored. Mercury in the flue gases can exist in three states, namely elemental mercury, monovalent mercury, and bivalent mercury. New ways to trap mercury are being discovered. Various mercury emission, reduction of mercury emission by dust removal system. Solid phase mercury is removed by the dust control system like scrubbers, fabric filter. Bag filters have the highest capacity to remove mercury. Mercury removal is much lower in a cold side ESP than in a bag filter. Removal of mercury is insignificant in hot side ESP. A low NOx combustion system along with bag filter is a good combination for removal of mercury. Wet scrubber can remove 90% of the oxidized mercury, but it cannot remove elemental mercury. Spray dry absorber type FGD system. If a spray dryer absorber is employed in plants fired by bituminous coal, it removes both the elemental mercury and the oxidized mercury. But in plants with low-grade coals, it removes only the oxidized mercury. Wet FGD is effective in reducing mercury emission in bituminous coal, subbituminous coal, and lignite fired units. Passing flue gases into the limestone through a sparger tube in a tower removes mercury in addition to SOx. Selective catalytic reduction systems convert elemental mercury to oxidized mercury, which can be removed by wet scrubber, but it works better in plants with bituminous coal than with subbituminous coal. A wet scrubber along with SCR is a good combination to remove mercury. The effluents from a scrubber should be sent to a settling tank, and a part of the decanted water may be recycled. We have Toxicon Technology, which claims to reduce mercury emission from coal-fired power plants significantly and also remove SPM easily, based on adsorption of mercury by activated carbon from gases whose bulk of SPM has been removed in advance by ESP or other dust collecting equipment. This ash or SPM can be used as usual without any danger of mercury pollution. Activated carbon is injected into the gas stream after the ESP ahead of back filter, resulting in efficient removal of mercury. Residual ash is collected in back filter, is suitably disposed of. There are two options. One is that we inject solvent ahead of back filter after the cold side ESP, or the other option is that we inject solvent after the hot side ESP and air preheater ahead of back filter. There's another technology, another method available that we inject calcium chloride for reducing the mercury emission. Inject calcium chloride in the coal to increase chlorine content before the coal preparation, pulverizing, and firing into the furnace. And spray dryer absorber is used to absorb SOx by lime. Activated carbon is dosed in the flue gases between SDA and back filter for absorbing mercury. Flue gases, after passing through the SDA, are led to the back filter. As you can see in this figure, the calcium chloride is injected in the coal preparation here, and then the activated carbon is injected ahead of the back filter. There is yet another method of electrocatalytic oxidation. In some cases, traditional pollution control technologies such as wet scrubbers and SCRs are not feasible. As ECU process combines 4 pollution control devices into a single integrated system that can be installed after power plant's particulate control device. Major reductions in the emissions of sulfur dioxide, NOx, fine particulate matter 2.5 microns, and mercury. These major reductions take place in SOx, NOx, fine PM 2.5, and mercury. Further, ECO2 has developed a technology which is a regenerative process that uses a proprietary solvent to capture carbon dioxide from the flue gas. After the capture of NOx, SO2, mercury, and fine particulate matter, the proprietary solution is regenerated to release carbon dioxide in the form that is ready for storage or beneficial use. ECO system produces ammonium sulfate as the fertilizer, which makes it economical over conventional technologies. ECO system also removes other materials, other metals and acid gases such as sulfur trioxide, H2SO4, sulfuric acid, and hydrochloric acid. Ammonium sulfate fertilizer is a co-product which is unique to the ECO system. If you look at the mercury removal performance of various equipments, cold side ESP can remove up to 40%, hot side ESP can remove up to 2%, fabric bag filter can remove up to 80%, spray dryer and plus bag filter can remove up to 80%, and wet flue gas desulfurization up to 58%. For subbituminous coal, the figures are also given, but the maximum of these is fabric bag filter can reduce, fabric bag filter can remove up to 60%, and wet flue gas desulfurization can remove only up to 15%. ECO electrocatalytic oxidation. Here, the major reductions in emissions of sulfur dioxide, NOx, PM 2.5, and mercury take place. It produces ammonium sulfate as the fertilizer. The regenerative process can capture carbon dioxide from flue gas and also removes metals and acid gases. We now talk about air quality management, which refers to all activities a regulatory authority undertakes to protect human health and the environment from the harmful effects of pollution. If you look at the air quality management cycle, we have to establish the goals. We have to determine how much reduction of pollutants we have to make and what are the control strategies, develop the control strategies, implement these programs, and undertake ongoing evaluation to make sure that the pollution levels are kept under control. The basic elements of an air quality management system are ambient air quality standards, NAAQS, the air quality monitoring standards, information about pollution sources and the amount they contribute to ambient air pollution, emission inventory, comprehensive listing gives the comprehensive listing of pollutants from all sources in a geographical area during a period of time, urban air quality management strategies, and assessment of air pollution exposures. To finally conclude, India's rapid economic growth has beneficiated the country in many ways, but it is clouded by the degrading environment and scarcity of natural resources. Coal-based steam power plants are the dirtiest energy source and a silent killer. Coal constitutes about 66% of the fuel used to produce roughly 210 gigawatts of electricity. Plant capacity additions 76 and gigawatts and 93 gigawatts were planned for 12th and 13th plants, but these plants were basically gotten rid of later on. There is a lack of policy attention towards the modern pollution control technologies. Evidence of pollutants entering the food chain and the human body, leading to serious health problems. Air quality management should ensure to help protect human health and the environment from the harmful effects of air pollution. Thank you for your kind attention.
Thank you very much for your nice presentation. It is really a wonderful session in which you have highlighted all the challenges in context to air pollution, especially in the sector of thermal power stations. Indeed, we all know that nowadays, from last couple of years, we are suffering from pandemic, and this COVID pandemic realized us to make our lungs healthy, and healthy lungs can only be possible with healthy air. So you discussed about the control of NOx, SOx, various nanoparticles having size less than 2 or 2.5 microns, and they are having huge concentration in our air. And for that nanoparticles or pollutants, these NOx, SOx, and nanoparticles are huge surface for shelter. These viruses can easily have shelter on these particles and can affect our health badly. So we really appreciate your efforts for sharing such a practical solution to reduce the NOx, SOx by various ways. You suggested us to reduce the NOx by using low NOx buried reburn technology, post-combustion NOx reduction. Oxide of sulfur can be reduced or removed by various methods. So they are really dangerous for our health system. I am sure that all the candidate participants are really enjoyed this session, and they are definitely benefited by attending this session. And they will be now conscious about improving our environment to provide the safeguard of environment so that our next generation will enjoy the health. And on behalf of entire team of IIM Jaipur and Nirwan University Jaipur, all the delegates, participants, I am highly thankful for your informative session. We wish and expect that you will continue with our journey, and in near future, if we require your kind guidance, kind lecture, you will be available for the same to us. Over to you, President Sir. We wish to have a formal photograph of this program, if with your kind permission. Over to you, please.
Yes. Excellent session. We are very thankful to Professor Kant. Thank you, sir. Thank you so much. So yes, we can have a group photograph.
If sir can stop the sharing this screen, we will have a wide photograph. Sir, please, can you stop this sharing?
Yeah. Thank you, sir.
Yes, I request all the members to please turn on your video so that we should have a good photograph of this program. So one more photograph. Just a minute. I also want to take photograph from FB. Thank you, sir. Thank you so much. Over to you, sir.
Thank you, everyone. Thank you so much. Happy Engineers Day.
Happy New Year's Day to all. It was nice hearing Professor Kant. Really great indeed, sir.
Thank you,
Delighted.
Martin.
Thank you very much.
So good indeed, sir. So lovely presentation, such an educating and deep insight. Really great indeed. Thanks a lot, please.
Thank you very much. You're welcome.
Thank you, sir. Shall we exit the meeting formally?